Alright guys, welcome to 3.1.2. We're going to be talking about rewriting expressions today. So to start off, we're going to be taking a look at problem number 13 here. So this is a very common thing that drives every high school math teacher insane, and that is students trying to make this turn into this. Right? So we need to find a counter example for it, or kind of find a way to prove it wrong. Right? So we could do that either by finding a counter example for it. So hey, here's a value of x and y which makes it not true, and therefore we can't say it's true because it's not always true. Or we could take one of them and rewrite it and show, hey, these are just two different things that cannot be changed to be equivalent. So that would be the other option there. So I'm going to go ahead and do this. So if we take a look at paper here, so if we have x plus y squared, and we're trying to say, hey, is that equal to x squared plus y squared? Well, to do this, I actually want to treat it like it's x plus y times x plus y and FOIL it out, right? So when I do that, I'll get x squared plus xy is 2xy plus y squared, right? So right there, I've kind of algebraically shown that, hey, this doesn't work, right? Because I'm saying x squared plus y squared equals x squared plus y squared plus 2xy equals x squared plus y squared. Now that's only ever going to be true if this is equivalent to 0. Now there's a whole lot of values of x and y which make that not 0, so it's not always going to be true. The other thing which we do is do a counter example for it, and I can say, well, let's do x is 1 and y is 1. 1 plus 1 is 2, 2 to the second is 4. Awesome. Here, 1 squared is 1, plus 1 squared is 1, 1 plus 1 is 2. Well, 4 is not the same as 2. Done. My counter example has proved it to not work. And then, but then we're asked, well, is there any times when this does work? So like I mentioned, this is going to work whenever this middle value is 0. So that's going to happen when like x is 0 or y is 0, right? So if I do like x is 0, y is 2, well, that's 0 plus 2 is 2. 2 squared is 4. This would be 0 plus 2 squared, which is 4. 4 is 4. Hey, it works. So it works for some very niche cases, but it does not work for everything. So that's one of those it's sometimes true type deals. All right. So now let's take a look at number 14. So this is bringing in the idea of the area model. Now this is going to look basically like factoring because effectively it is. So we can use this area model to say, well, this and this are equivalent because I can say, well, 2x minus 3 and put that on the bottom, 3x plus 1 and put that over here, and then if I multiply those, I get this, and then combining my like terms, I end up getting 6x squared minus 7x minus 3, right? So some people draw their boxes differently. Like I will always put this dot on the bottom, I'll put it on the top. It just kind of moves around the box a little bit. It does the exact same thing. So if you see me do it differently than the book does or that you learned, it's okay. It's just putting those in a different place. It's just kind of personal preference / how you learned. So don't feel like you have to do it the same way you see me do or the book do or whatever. Okay, so that's kind of effectively how this works. And again, you probably have done this a bunch when you learned how to factor with the box method. So we're going to try and use that kind of to effectively do these problems here. So part B here, we're going to try and find an area model that will express this. And then we're going to try and find an area model that will express this. So let's go ahead, hop back over to my doc camera, and we'll look at those. So if I have 5k minus 3 times 2k minus 1, right? For my box, again, I'm just drawing it a little bit differently than you might, but this is just how I always have done it and how I prefer it. So then this times this is going to be 10k squared. This times this is negative 6k. This times this is negative 5k. This times this is a positive, oops, sorry, positive 3. So the equivalent statement would then be 10k squared minus 11k plus 3, because again, I'm combining these as my like terms. So not too bad, right? That's effectively multiplying, which is really, really easy for us to do. One that's a little bit more challenging is if we try and do it the opposite way. So we're trying to factor these apart. So here they give us x squared minus 3x minus 4. So I know that my x squared is going to go here. Again, if some of you probably learned how to factor it and you put it on the bottom, the exact same thing. It's just kind of put it in a different spot. And then my minus 4, put that here. And then I say, well, what is going to multiply to be this, add to be this? It's 1 times the negative 4, but that doesn't change anything. So to multiply to be negative 4, add to be a negative 3, well, that's going to be a negative 4 and a positive 1. So negative 4, positive 1, I'll tack on the x's. So then I can kind of do that greatest common factor out. So here I can pull out an x, here I can pull out a negative 4, here I can pull out an x, here I can only pull out a 1. So then that factors into x minus 4 and x plus 1. So that is effectively the process. Okay. All right, so let's take a look at number 15. So we're trying to effectively go back and forth depending on the ones which we're going to be doing here. So I'm going to have you go ahead and pause this, try those out, and then I will come back and I will do some of those, probably not all of them. Okay, so the ones that I want to focus on, I want to do B, C, and D primarily. So if you take a look at those, let me pull up my document camera. So on B, we have 3x minus 1 times x plus 2y minus 4. So we can still set up the box. It just becomes a little bit larger of a box because now we end up having 6 little places in it, not just the 4. Okay. And really, once you get past a 2 by 2, like where it's just that, the 2 by 2s you kind of use that FOIL method to kind of shortcut it and get there a bit faster. But once you get more than that, I typically just go straight to a box. Maybe it feels a little bit like childish, but like it's way faster and way easier, especially when you have like a 3 by 3 or a 3 by 4. It's way easier to go with this kind of stuff. And it's more organized, you make way less mistakes. So 3x times x is 3x squared, and this would be negative x. This would be 6xy. This would be negative 2y. This would be negative 12x, and this would be positive 4. So like term-wise, it's a little bit more challenging here, but I see I have a 3x squared, and then I have my xy, which is going to be plus 6xy, and then I have my x's, which is going to be minus 13x, and I have my minus 2y, and then I have that plus 4 as my constant. So those are all of my like terms. So again, kind of messy, but it's way easier, and I have a much lower chance of actually missing things if I do it in that actual box for me. All right, then we're going to take a look at C and D. So on C, we have x minus 3 times x plus 3. So x minus 3, x plus 3. Draw out the box for it. And I get, well, this is x squared, this is 3x, this is negative 3x, and this is negative 9. So that turns into x squared. Those two parts cancel out when I combine those like terms. So I get minus 9. Right, and then on D, I get 4x squared. So if I drew out my little box, as I'm trying to go the other way and factor it this time, 4x squared, and then negative 49. I'm now taking a look at that and saying, well, how do I multiply and get negative 49 and then add and get 0? Because there's no b term there, so your b is 0. So I need to multiply to be this, add to be 0. Well, the only way to add to be 0 is if I have the same number and one's positive and one's negative. So they're both going to have to be 7, 1 negative 7, 1 positive 7 to get that negative 49. So negative 7x and positive 7x. So now when I pull out my terms here, I can pull out a 7 here, and here I can pull out a 7. Now it becomes a little bit more challenging here because here I really want to pull out a 2x and a 2x. I made a mistake because I forgot to do the 49 times the 4, which actually makes it a little bit more challenging. So if we do that, getting a ahead of myself because I know the shortcut for it. 49 times 4. All right, so I get 196. So the numbers that are going to multiply together to be 196. Well, if I square root 196, I get that it's 14. Okay, so really what I want here is negative 14, positive 14. That's my bad. I was trying to shortcut it without really thinking it through. So I can pull out a 7, a negative 7 from here, positive 7 from there, and then I can pull out a 2 and a 2. So I end up getting 2x minus 7 and 2x plus 7. Now those two I chose specifically because those are a very important pattern, which we're going to be learning the shortcut for here in a little bit. But we should notice that, hey, both of those middle terms cancel out, and that is a pretty important thing that can help us out in the future. Okay, so let's take a look at number 16. So first of all, are these going to be able to be written in the area model? Well, on A, we can't do it as is in an area model because we have 3 things being multiplied. So you would effectively need like a 3D model or like a volume model. But the easier way to do it if you really wanted to get the area model would be to take this p and multiply it through to all of this and get p squared plus 3p and then multiply that by the 2p minus 1 in an area model. Right? So that would be how I would recommend doing that one. Then over here on B, we can't do the area model for the entire thing because of this plus sign. I could do it for just this part over here, and then I could just add that to that. And that is, again, what I would recommend doing. So let's go ahead and do that out. So if we, on that first one, if I do P by P plus 3, so I'll do 2 really small area models here. And you probably don't need to do an area model here, but I'm just trying to show you the process. P squared and 3p. So then I'm going to do p squared and 3p times the 2p minus 1. So then this gives me 2p cubed. This would be 6p squared. This would be negative p squared. And then this would be minus 3p. So I still have my like terms there. So I overall get 2p cubed plus 5p squared minus 3p. Right? So not a huge deal. And then on the other one there, if I do the x by x plus 1, again, you'd probably just do distributive property, but I'm trying to show the area models because it's really trying to push that right now for reasons which will become apparent soon. This will give me x squared and x. So then I have x squared plus x plus 3x plus 5. Sorry, 3x minus 5. So then combine my like terms here. Well, that's just going to be x squared plus 4x's minus 5. So again, not a huge deal there. They're just trying to show, hey, here's times when you really can't use just straight area model. You can still use it, but you have to do little parts of it or just manipulate it a little bit more. All right. So last thing we're going to be looking at today is going to be 17 and 18. So on 17, they're giving you parts of an area model, and they want you to fill in the other parts. So for instance, like on C here, we want to know what would go here, what would go here, what would go here, and then what would go in each of those three spaces. So try and use some deductive reasoning to figure out what would need to go into each of those different places. And then I'm not sure why on A they put the 3 here as opposed to putting the 3 here. Pretend like this 3 is down here. The book did it. I'm not sure why, but there you go. So put the D3 there and then figure out what, and then fill out all of the missing areas for all of these ones, and then come back and we'll talk A about those. Okay, so what we should find here is, well, it's pretty easy to figure out what needs to go here because x times whatever this is gives me xy. So this has to be y, right? So then y times 3 is 3y, and then what has to go here would be, well, y times y is y squared. So that would fill in my entire box there. Over here, well, I know that the only thing common here is that x, so I'm going to have an x here. And then 3 times this here. Well, x times this gives me 8x. So this has to be an 8 here. So then 8 times 3 gives me a 24 here. And then this would have to be an x because x times x gives me x to the second. So then this over here would be 3x. Right? So it's about that deductive reasoning to figure out, hey, what goes in which place. If I look down here on C, right? Well, if this is 3y times, negative 3, negative 3 times negative 4, this would be 12y, so it's positive, right? So then I can say, well, this times what would give me this? Well, I'm missing an x, so there has to be an x over here. And then to get negative 20, this has to be a positive 5. So this would be a 5x over here, right? So then I can say, well, then what has to be down here? Well, this times negative 3 would be, actually, this one I'm just going to draw because it's a little bit more building on stuff here as opposed to me trying to say it all. But hopefully the first two were simple enough that you could get just from me talking to you about it. All right, so let me draw out what we know, because once we fill in the parts, we figure out it makes this a lot easier to explain. So this is negative 3, this is negative 4y, this is negative 20xy, this was negative 6x, and this was negative 15. All right, so we said, well, this here is going to be this times this, which is going to be 12y. All right, well, this times this, this times this has to give me negative 20xy. So I'm missing an x and I'm missing a 5. So this will be 5x here. So then I can figure out, well, what's going to be here? Well, this is negative 3 times what gives you negative 6x. Well, I'm missing an x, and I'm also missing a 2, so this would have to be a 2x. The negative 3 times what gives me a negative 15? Well, that's just a positive 5. So now I can figure out these. Well, 5x times 2x is going to be 10x squared. And 5x times 5 is going to be 25x. So there you go. Once you can kind of use that deductive reasoning, these go by pretty fast, and it's not too bad. All right, and then the last one over here, if this is an x times what gives you x squared? Well, then this here has to be x, right? Oh, sorry, they're doing it in a slightly different order here. So yeah, so they have x here. And then, well, this 12, we're going to have to break it up. And we can do this a number of different ways, right? We could have it be 12 and it's like 12 and 1 or 3 and 4 or things like that. So there's a number of different options once you get to that part D, because again, we don't have anything else which is going to be kind of telling us that, so we can kind of break it up any way which we want there, because we don't have anything set to be here or here. Okay, so then on number 18. So this is referring back to parts C and D in problem number 15. So if we take a look at those again. That was these two here that we kind of noticed that the middle numbers kind of canceled out. So there was a pattern. So what was the pattern which we noticed? So let's go back and look at those on this form here. All right. So let's take a look at how does this relate to where it came from. So we got x squared minus 9, and I had x and 3, x and minus 3. Okay, here I had this was 4x squared minus 49. So that gave me 2x and 2x, so 2x and 2x from the 4x squared, negative 7, positive 7 from the negative 49. So what patterns do we notice? Well, first of all, this square rooted gave me this and this. Likewise, this square rooted gave me that and that. Right? Also, this square rooted gave me this and this. This square rooted gave me this and this. Right? And the other thing which was common was that these were being subtracted. And then that made the other parts be one's negative, one's positive. One's negative, one's positive. And that is effectively the pattern. This is called the difference of two perfect squares pattern. You've probably heard about this a little bit in the past, but it shouldn't be entirely brand new for us. But we're going to try and reinforce that here. So let's hop back over to this. So let's try that pattern out and see what can we do for this and these two. So we're going to do this first one together, and then I'll have you try those other two just using that shortcut. So first one we have is w squared minus 81. Well, if I follow my pattern, this first number is just the square root of this. Well, square root of w squared is just going to be w. And then the square root of this is going to be 9. So that goes here and here. And then one of those is positive, one of those is negative. There's my pattern. And it works because of that being negative. So really, that's crazy easy and crazy fast. So let's try that out on the second and the third one. See what you can do there. Go. All right. So what we should get on the first one is 4m squared minus 1. So that would factor into, square root of this is 2m, and the square root of this is 1, 1 and 1. One of those is positive, one of those is negative, we're done. It's that easy, right? And the last one over here, we have, make that a little bigger so I can see it better, x squared minus 16y squared. Okay. So when I factor that, square root of this is going to be x and x. Square root of this is going to be, well, 4y. And then one's positive, one's negative. Done. Okay. So again, the big thing that I want to reinforce right now is that this is going to work if the following criteria are met. The first term is a perfect square, meaning I can square root it and get a nice pretty thing out of it, right? The second term is a perfect square. Again, I can square root it and get something nice and pretty out of it. And it is being subtracted. You need to have all three of those criteria met if you want to follow this pattern. Now, technically, they don't have to be perfect squares, and you could leave radicals here. But we really don't like to factor and have radicals in our factors, so we try and kind of avoid that case there. But they do need to be subtracting. If it's being added, this pattern does not work. Okay, so just keep that in mind. All right, with that, here is our homework for 312. This is only day one. There is going to be a second day. So I will talk to you guys next time.